I guess I gotta see where this is. I think I'm probably, yep, I'm up and running. I don't know why it hides itself behind that first page, but okay, up and running. So this is kind of a lecture, and I didn't give it a name because I don't want to tip my hand as to what we're looking at. I want you to try to figure out what we're looking at as we go along. So it's an introductory lecture, but it's going to cover a wide range of topics. And I don't rehearse any of these videos. I just, turn the machine on and go at it. So I did put some things down at the top of the board here. And I've got some notes to myself about the kinds of questions I want to ask. Because my memory is just not what it used to be. And I want to try to cover a certain number of topics. So let's have at it. And first question, what are you looking at? Okay, so each question that I ask, I hope you pause the video, and I'm going to ask a series of questions and develop a few concepts along the way. Get you to think about some things that are important. All right, so you're pausing the video. I hope you said that you're looking at volume. These are called cubes. All right, so we're looking at cubes, and cubes have volume. And that volume comes from length times width times height. Now, these are special cases because length, width, and height, they're all the same. So I'll refer to these as perfect cubes. Okay, I guess that makes sense. And in your earlier studies, you were working with squares. And if we put 6 squares together that are all the same size, we get a perfect cube. And squares are rectangles, and that topic is called quadratics, 4-sided figures, quad, Latin for four. All right, and one of the major things that you did in that series of problems involved in quadratics was complete the square. All right, and lo and behold, you can do the same thing with cubes. Doesn't seem to be in the textbooks, but there's a video somewhere in all the ones that have done completing the cube. I suggest you look at it. And because I'm not going to take the time to complete a cube here. That takes 5 or 10 minutes. This is going to be a long video anyway. Right? So you're looking at cubic relations, and what do we do with relations? We graph them. So can you look at this and then sketch what you see? All right, and I've asked you a question, so you're pausing the video. I'm just going to keep going. Well, sure looks like, using Rene Descartes' coordinate system, we can put side length here, the sides of the cube, and the volume of the cube. Okay, it looks like a -3. Let's say that that's -3, and we'll estimate from there. Maybe I can go a little further. Let's say that's -3, and -3 times -3 times is a negative number. Let's go down 27 units. And let's get our first coordinate. All right, and let's just put the y value here, -27. And then -2, I don't know. That's halfway, so 2/3 of the way, maybe there. -2 gets us a volume of -8. That's about 1/3 of the way. Over here, okay, I gotta look at this from here. 1/3 of the way, maybe there. Okay, I'm estimating, of course. And so that's some change. That's the average rate of change from here to here is up 19 units with one side length change. And then at -1, we're at -1, so I'll put -8 here. All right, and -1 might be somewhere in there. -1, and from -8 to -1, the average rate of change is 7 units, up 7 units. And then we go to 0, and then we go to 1. That's a little too big. Then we go to 1, and that's a little better. And then we go to 2, and then we go to 3, and we go to 1, up to 8, up to 27, and again, average rate of change, up 1, up 7, up 19. So there's some symmetry of sorts here, right? It's an odd function, by the way. F of x equals minus f of x. Might as well say that. The definition of an odd function is that would be true. Right, so what is f of -2, -8? What's the opposite of -8? +8, up, right there, so that's a y value of 1, y value of 8, a y value of 27, excuse me. As I said, I haven't done any of these out already because I wanted to go with you. Now, these are average rates of change, right? This is a continuous function. Looks something like that. And this obviously continues down, yes, and goes up. Where does it go up to? Infinity. And we talked about that in an earlier video. I forget which one yesterday it was, but that was what was called the limit. Limit is y value as time, side length, excuse me. Do I have an eraser? I have one. I gotta get another one. That's too bad. I'll be right back. It's right here. Okay. So as the side gets bigger and bigger and bigger, as in goes to infinity, as the side length goes to infinity, why do we call it x now? Then my y values, which are coming from the cubic process, right? That's the cubic process, appear to go to infinity themselves. And if we look backwards, as our x values go to negative infinity, blah, 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 the y values are going to negative infinity. Okay, and I think you should hear that, because that's the first topic you cover in a calculus class, and there's no reason I couldn't say that to you now, which means your brain starts processing it. It's a language. Okay, I'm not going to hide that from you. Now, we were a little bit discriminatory here in our graph. Okay, pause the video. What do you think? Well, I could have made the y-axis my side length and the x-axis my volume. And what did I just perform? Inverse operation. So instead of a 3 getting us a 27, which may be out here somewhere, gets us a 3. Okay. And what is it going from volume, might be easier to see, to the number 2? What is this side length called? Well, if you said the cube root of x, you would be right. So what do we put inside that radical symbol? Volume. The cube root of the volume gets us the side length. And it turns out that that graph, and I'm not going to spend much more time on it than this, but that graph, let me do it over here very quickly, looks like this. That's what that graph's going to look like. All right, and same thing's true. As I head to infinity, this is always going up slowly. Instead of going up fast, the inverse is going up slow. Okay, but the limit as x goes to infinity is also infinity. And as x goes to negative infinity, it's also negative infinity. It just doesn't look that way. But that's all, you know, the cube root of 64 goes up by 1 when you go to the cube root of 125. A 4 goes to a 5. Forget 6 times 6 times 6. I should know it. 216, I think. The cube root of 216 is 6. 5 went to 6. X's are going up. But the X's are what? The X's are numbers like 8, 27, 64, and then they're going up by 1. All right, getting off topic here. Well, maybe not. It's important to know that. So what are some of the things we're going to do with this topic? Okay, let me see. I talked about limits. Oh, domain and range. Let's just go back to x cubed. All right. What side length can I cube? Can you do 7 times 7 times 7? Can you do a billion times a billion times a billion? Can you do 0 times 0 times 0? Can you do a half times a half times a half? Is there any number and -2 times -2 times -2 could do it with the negatives? I don't think there's anything I can't use. So the domain is all reals. And the y values are going from where to where? negative infinity to positive infinity. So the y range is all reals. Get all the numbers in, put all the numbers into this function. You can draw these for any side length and you're going to get a value. All right, so that's domain and range. Get that out of the way. All right. Okay, so x cubed, cube root of x, right? A couple of graphs that come from this correlation here. And what are these operations called? Inverses. What do we use inverse operations for? Well, we can solve equations. What's the next way to solve equations? Products. And there are some interesting products that come out of this. For instance, 27 minus 8. I can write that as a product. It turns out it's 3 minus 2 times 9 plus 6 plus 4. Check it out. I just changed the difference of two cubes into a product. Or I could have added them up. I could have done 27 plus 8 equals 3 plus 2 times 9 minus 6 plus 4. You check that one out. Okay, we're going to learn how to factor the sum and difference of cubes. And if you pause the video and look at that, that's where this is different than, you know, your typical language, probably vous français, mais oui. Yeah, you got to do some thinking. You have to look for patterns. There's significant patterns here. All right, what is the relationship between 7 and 3? Cube roots. So once I get the cube roots and the appropriate sign, something's happening in that second parentheses that I think if you look at it, and if you don't look at it, don't expect to get it right on tests. That's how this works. But we'll be practicing that every day now for the rest of the semester. All right, and I'll do, you know, rapid fire 5 with a bunch of them, but not right now. We're just getting an introduction to cubics, and our introduction is going to get a little deeper. Yeah, the time to get deeper. Inverse operation, AR, average rates of change. I talked about that. Oh, instantaneous rates of change. Well, I know I'm going up at 19 to 1 from that coordinate to this coordinate. My x's, this was a -2, this one was a -3, right? My x's have changed by 1, and my y's have gone from -27 to -8. So -3 to -2 is up 1, -27 to -8 is up 19, so that's the average rate of change. Okay, but what's happening instantaneously? Rates of change, y2 minus y1 over x2 minus x1. All right, what we do in calculus is we take a microscope to this, not a big jump, but a little jump. So let me, where can I do this? I'll do it here. I'll make some space here. Oops, hope I don't forget the things I want to tell you. So let's look at how things change in 2. And I'll do 3 decimal places. 1, 2, 3. I could do 30, doesn't matter, right? 2 cubed is 8. And there's a nice pattern here for geometric reasons, so we're going to look at that in a minute. So if I cube this, I get 8 point, let me see, make sure I got this right. Yeah, 8.012006001. All right, and I don't have computer graphics here, but I do have something that I'll show you in a moment. I should show it to you now. Okay, so here's my attempt at a cube. This is one of the boxes that the refills to the markers come from. So there's my cube. We're going to pretend this is a 2 by 2 by 2. Okay, 2 by 2 by 2. 8 units of volume here. And if I do this, if I put a sleeve, right, here's the sleeve. Notice it's got 3 sides, right? And I slip it onto the box. There it is. I've just added a little volume to the box. What volume did I add to the box? There it is. And remember, volume is length times width times height. So what is the length? 2. what is the width? 2, I'm losing sense of my next, I think that's the height, 2, right? So there's a 2 by 2 here. And if you multiply 2 by 2, you get what? Area. And that area is 4 units. And that area is 4 units. And that area is 4 units. Wow, 4 plus 4 plus 4 gets you 12. Must be an accident. Yeah, but where's the height? And I told you, you got length, you got width, where's the height? Can you pause the video and think about it? It's the thickness of this paper that I used as a layer. It's the thickness of the paper. And there are some overlaps here that are not part of the volume. Okay, and that's what's the error is the rest of that. But that is really how this is changing in terms of accumulation of volume. And if I divide 0.012, I don't have my marker anymore, 0.012 by 0.001, it's going up to 12 to 1. And guess what? Those 3 squares times that little change in x gets me my change in volume. And what happens when you take a change in volume and you divide it by a change in x? Don't we get a y2 minus y1 over x2 minus x1? So really, this thing is changing at this instant. It's going up. This is where I am. At this instant, this is actually going up to 12 to 1. And can you see that it's not going up that fast as I approach 0? That's just not happening. Why? Well, the surface area of the cube has a lot to do with the rate of change at an instant. Well, what about the surface area here of this cube? Well, there isn't one. There isn't one. So it can't be changing much, right? Because we're always going to change by, in our case, we'll just change by 0.001. We could have changed by 0.001. Okay, and so these are some of the calculus concepts that come in your way. And I got to be honest with you, you need to think about these things before you take your first year of calculus. Right? You got to start processing these things so that when you start working with calculus, and all I did is take and call this dy dx, its rate of change, small differences, right? Small differences in x, 3x squared. Okay, and you'll learn more about that when you get there, but I just want to put some thoughts in your head. And if I kept putting layer after layer of volume on it, so let's go layer of volume, right? Layer of volume, another layer of volume, and I kept doing that, this box is growing until it gets to be what? That 3 by 3 box, that bigger volume. All right, now what am I doing there? Well, in calculus, we have this symbol. Kind of looks like an S for sum. If you add up each of those layers from 2 to 3, you actually get the change in volume. And this is the notation you'll see eventually. That's a 2, right? And what is the volume of a 2 by 2? 8. What is the volume of a 3 by 3? 27. And you actually get 19 units of volume in that add a layer, add a layer, add a layer. Right? You get 19 units of volume. Yeah, that's where you're headed. Those are the kinds of things you're gonna. And it turns out that the area from 2 to 3, right, under this curve will get you those 19 units of area. Okay, or 19 units of volume. If we multiply, I'm getting way ahead of myself here. All right, but that's coming your way. This kind of geometric work is the origins of the study. Okay. All right, so now what else do I want to say? Oh, I should give you the a 3 by 3. Boy, what a Jackson Pollock this is. All right, so let's do 3, gets me 27. And let's do, why don't we do 6 decimal places? That's going to be 18. Oh, God almighty, let's try. 3.1, 2, 3, 4, 5, 6 gets us 27.1, 2, 3, 3x squared is the derivative. 3 squared, 27. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 3 times 3 is 9. 1, 2, 3, 4, 5, 6. Now I'm not using a calculator, but you can go check that. And so how is it changing? 1, 2, 3, 4, 5, 6. Let's get rid of this. Dot. Let's get rid of the 27. 1, 2, 3, 4, 5, 6. Looks like it's 27 to 1. And the side length's 3. And 3 times 3 squared tells us that at this instant, where am I? That's 8. At that instant, I'm going up at 27 to 1. At this instant, side length of 2. I'm going up at 6 to 1. At this instant, side length of -3 times -3. Again, I'm going up at 27 to 1 at this instant. An average rate of change in 19, does it look like my average rate is somewhere between 12 and 17? I hope so. Okay, have I missed anything? Oh, yes, there's still more to be talked about. All right, I guess I've got to erase some things here, obviously. And I'll come back to, and this is an important part of this discussion. And I don't think it's in the textbooks. All right. There's our basic cubic, right? Where is it changing least quickly? Right there. Right. Why? No surface area accumulation. Okay. So there's no box there. All right. We call that a point of inflection. Point of inflection. Okay. And that's where this graph goes from a concave down shape to a concave up shape. All right. Remember, the rates of change were decreasing. Right. Remember, we were down here at 27 to 1, and then we got to here at 12 to 1, and at 1 it's 3 to 1, and here it's 0. I'm not changing much at all. So my rates are declining. If we put tangent lines here, we get a sense of things decreasing. Whereas over here, our rates go from 3 to 12 user-friendly numbers to 27. Right, they're going up. And so where that transitions is from concave down shape to concave up. Well, how do you find a point of inflection easily? Well, we've got volume over here, length times width times height. Right? And when does the volume equal 0? When one of the dimensions equals 0. Okay. And how did you find the point of inflection? I'm sorry, how did you find the vertex of a quadratic? I hope your brain is saying minus b over 2a. We said why you've done that. And we're writing our linear functions as a x minus h plus k. Okay, and where does that equal 0? Minus b over a is where a linear function goes from negative to positive or vice versa. Minus b over 2a, x minus h squared plus k. Vertex is at minus b over 2a. You want to guess how you find the point of inflection? If you said minus b over 3a, you would be right. Minus b over 3a. And this is all about changing a rectangle into a square area statement with a constant. Right? That's what that's about. So guess how you get minus b over 3a. Make a perfect cube. And there's a video on that, completing the cube. I think I mentioned it earlier. And by completing the cube, you can start to put these in graphing form. That's another half-hour discussion, and it's there if you want to learn it. Okay, I don't think it's in the textbooks. All right, but the graphing form for cubics is ax minus h cubed plus a multiplier times x minus h plus k. Okay, and minus b over 3a is what unlocks that. Okay, how do you find minus b over 3a? The same way you find minus b over 2a. You take the length, the width, h, divide it by 3, which is evening off the sides of a cube that's not a perfect cube. And we make one, and then it's a little more complicated than the quadratic. Right? And I think I talked about it in the putting cubics in graphing form video. And I'm trying to put these now in categories. I'm calling it library series. So I'll have to go look for that one. I'll have to call it cubics, putting cubics in graphic form. Okay? So let me just give you the quick one that I did on that. The quick one had zeros at 0, 2, and 10. Right? If you add those up and divide by 3, you get 4. Well, here's 4. Boom, something like that. Can you see the concave down, concave up? That's just leading you into what's going on a little bit. Okay, I hope I said everything that I wanted to say. I'm sure I didn't. If I've made this video and haven't made a mistake, it might be the first one I've ever done. Usually I make a sign error somewhere or whatever, but this gets the conversation started. All right, and that's all we're doing is getting the conversation started. Then we're going to work with it the rest of the semester. All right, and give you a chance at working knowledge so you can take it into your next class. All right, it's a long video, but the higher you go up the ladder in this discipline, the more you got to be patient, reflect, what's going on here? Let's talk about it again. All right, have a good one.